There's an actuary talking now. This room used to be full. And they were just all hightailing it out. Green button, move slides. There we go. Hi, my name is Kevin Burke. I'm a property casualty actuary. I'm a member of the NAIC model review team. And today we're going to talk about missing data, which has been a hot topic for probably a year or so by now. A little bit about me. I've been a P&C actuary. I'm a fellow of the Casualty Actuarial Society for about 25 years. Prior to that, I was in academics. I have a PhD in mathematics and taught, but you get out of teaching because insurance pays more. So I work with a bunch of great people, a bunch of really smart people. Every day is a blast. I got a great manager, so this is like a really cool job for me. I don't know about whether the rest of you have cool jobs, but I really enjoy what I'm doing, and I've really had a good time learning about missing data analysis, and hopefully I can get some stuff to share with you guys. Okay? So there's the big fuss about missing data is that companies want to rate on characteristics that are missing. We're not going to talk about that. The two major things that we talk about are if you have missing rating variable, you don't know how old the house is, for example, can I have a rating factor of 1.00? Another thing that comes up is on the consumer aspect. If a consumer finds out that maybe you don't have information about their property or they don't, they got the incorrect data, how do you get that fixed? That's another important issue. We're not going to talk about that either. Those are separate things that are going on, especially with regards to rating, that you're seeing regulations starting to spring up around the country. Okay? What we're going to talk about is the actuarial approach to building models when you have missing data. Okay, and when I talk about missing data, I'm talking about missing risk characteristics. I'm not talking about we don't know how much they paid for a claim, but they had a claim. So it's the things that actuaries will build models with to get rating factors. Okay, so brief outline, talk about when missing data first kind of reared its head in the actuarial business. We're going to talk about generalized linear models. We're going to talk about the current actuarial practice, which turns out to be statistically unsound. I'm going to give you an example. We'll talk about the different types of missing data. We'll talk a little bit about modeling with missing data as well. I put abbreviated in the slide title because I'm not going to put any equations. If you want to know stuff, I'm around till noontime on Thursday. Hit me up. I can give you some reference. We can talk a little bit more in detail about the modeling approaches. But I really wanted to keep this at a high level so that, you know, if you're a regulator and you get at one of these models with missing data, you at least have some kind of an idea, hey, here are some of the types of questions I want to ask. So missing data, well, sorry, I got ahead of myself. The statisticians have known about the problem of missing data for a long, long time. If they're doing a clinical study and somebody misses an appointment, they may have an observation here, oops, nothing, and then we've got another observation. Well, what do we do here? What was their blood level of something at a particular point in time? What if you're doing a survey? A lot of people won't tell you how much their household income is. So you may have a ton of information about a person, but then all of a sudden you don't have any information on this one variable that you want to analyze. How do you handle that? These are questions. Am I going too fast? No? Okay. these are questions that the statisticians have been dealing with over time. And they've come up with some pretty sophisticated approaches to dealing with it. And hopefully, I can share some of that with you. Missing data in insurance, in actuarial analysis in general, started in the early 2000s when credit-based insurance scores came out. Okay, for those of you that maybe are unfamiliar with what a credit-based insurance score is, the credit bureaus would take your credit information. How often did you pay this bill? Are you late on this? What's your ratio of available credit to used credit? Things like that. And what they did is they ran some models against insurance data, and they found out, well, the way people behave with their finances is a predictor primarily of the claim frequency, how often you will file a claim. And so what happened was these insurance scores were created. And they generally went, say, from 200 to, 997. And then the 998 and 999 were generally reserved not to give a number based on your propensity to file an insurance claim, but rather they were information that the credit score creators were giving to the people that bought the credit score. 998 said thin hit. I may have these backwards. 998 is thin hit, 999 would be no hit. And what those were no hit means, hey, we don't have any information about this person at all. 998 may be, well, we rate on about 6 to 10 different things, and we've only got 2. We don't feel comfortable giving you a score. That's what a thin hit would be. And so the rest of the numbers actually could be used in an actuarial model, but these mean different things. A lot of times, what would happen is the rating factor for these guys would be, say, for example, well, we don't know, we're going to give you a factor of 1.00, which is neutral. Maybe give a weighted factor. Take the average insurance score and give that indicated factor to the policyholder rating factor. Sometimes there would be specific jurisdictions that would say, well, if you have a no hit on a particular score, then their rating factor is 1.00. So there was a lot of that going on, but that was the first time that you actually saw missing data, is when the credit score vendor gave you these 2 codes and said, here you go, we don't know what's going on here, but we tried to score them. Okay? So then I'll blame it all on the actuaries, what the heck. When the actuaries went to rate, you started coming up with rational explanations as to why maybe you might want to rate them a little more. And it would be things like, well, they don't use credit. Well, everybody uses credit, so they're a little riskier, so we want to charge them a little more. Or, they don't have any information at all on their credit score. Well, then, these guys, we're really uncertain about them. We need to add a little bit of risk to it. Okay? But the default assumption was, while not spoken, was kind of the policyholder behavior is what is leading us to not know about these particular policyholders or prospective policyholders. Okay, what we're going to see coming up is that the lack of information regarding a policyholder, that's on the company. That's not on the policyholder anymore. You can't rationalize that. And I'll give you a very good example that's kind of modified from what we've seen. I'm not giving you actual modeled results or anything like that because we've got confidentiality. We review reports. They go to the individual state insurance departments. And so I'm not going to give you any numbers or anything. Everything's fabricated just to make a point so that, you know, we're not violating a confidentiality we have with all the different states and so on. Okay. So here's where the missing data is coming from now. Let's stand here. How's that? You can still hear me? Yeah. So the top table is insurer data. That's usually pretty good. The individual companies have data warehouse people that are paying attention to the data. They got controls as to when things get moved from, you know, staging into, you know, their production warehouse, for example. They're balancing loss information to the financial statements. That stuff's really good. The insurance company, though, wants a little bit more information about somebody. So this third-party vendor says, hey, I know a bunch of stuff about people. You give me their VIN, I'll tell you everything you want to know about the car. You give me their address, I'll go hit some public records, I'll tell you everything you need to know about the house. But the third-party vendors don't know everybody. So in this example here, we've got 3 policyholders, A, B, and C, and the company knows everything about them. And then the third-party vendor says, well, I can give you more data, and they're like, well, we're actuaries. More data is great data. But the third-party guy says, well, I just know about policyholder A and B. And the insurance company's like, okay, well, more data, great. Now here's what you've got. Your third party, you may not know something that you want to know about that one particular individual. And so when the people that are modeling get that data, they've got to figure out how to model with that. Now, the first part in a modeling process, if you sat a statistician down, an actuary down, and said, here's a bunch of data, build me a model. The first step is what's called exploratory data analysis. And it's exactly what the name says it is. You start looking, you know, you look at the data. If you can get it all in a spreadsheet, scan through the spreadsheet. Do a lot of summaries. If you've got losses and you've got policyholder age, well, see what the loss by age is. If you've got a territory, see what's going on there. Well, part of that exploratory data analysis is, if you've got missing data, how much is missing for a particular risk characteristic? Is 40% of the roof age values missing? Those are things that should be discovered during this exploratory data analysis. Okay, so that's important, and I've heard this misrepresented. Modeling with missing data is a modeling decision. Nobody's holding a gun to an insurance company's head and saying, use that data that you only know half of it. That's a decision made by, I mean, ultimately by the company, but by the data scientists and the actuaries that are building the models. Okay, and we're in the risk business. When you don't know something, you've got more uncertainty. So when you're building a model with missing data, you've got to be asking yourself, how do I understand the uncertainty that is coming in from having missing data in my model? And that's one of the things the statisticians have really come up with some good ideas on. Okay? Good on time? All right. We're going to take a slight step back to introductory statistics, non-calculus based. Okay? Because we need this one particular concept here of what an estimator is. Okay? So if I give you 2 dice, and I say, what's the chance, what's the probability of you rolling a 7? It's 1/6, right? You've got 1, 2, 3, 4, 5, 6 on one, you've got 1, 2, 3, 4, 5, 6 on the other. There's 36 different ways that can roll. 1 plus 6 is 7, 2 plus 5 is 7, and so on. There's 6 ways there. So 6 out of 36 gives you 1/6. That's the population parameter. That's easy to get. But in real life, we don't know a lot of population parameters. If I want to know the claim frequency, what's the relationship between automobile accidents for women versus automobile accidents for men? There's a number. But we don't know what it is. We're going to estimate it. We're going to get a statistic and estimate the population parameter. Okay? So we're going to do a little experiment. Imagine rolling, just sitting there at the table and rolling dice. You count the number of times you rolled the dice, you count the number of times you get a 7, and do the fraction. Okay, that's an estimator. So if you roll it once, it's either 0 or 1. Both of those are wrong. 2 times, well, it's going to be 0, a half, or 1. Those are wrong. But over time, as you continue to roll the dice, the more and more rolls of the dice you get, the closer that fraction gets to the actual value. Okay, so this is a simulation I did, and you can see the blue's all over the place for a while. And then it eventually settles down over time, and you get to the, you get really close to the actual value. Okay, that's what statistical models are doing. If I have gender in a generalized linear model, for example, I'll get an estimate for the relationship between, say, male and female drivers. If it's a frequency model, then what's the claim frequency? Okay, this estimator is what's called unbiased, because the estimates head towards the actual value. You can imagine estimators that maybe don't head towards the population parameter. Okay, and so in statistical terms, the expected value of the estimator is the population parameter. Okay, E of beta hat equals beta, something like that for the statisticians in the room, right? What's important, and we get to our first actuarial, maybe only actuarial statement really, the actuarial standards tell you that when you're using estimators, they have to be pointing towards the actual expected cost. When you build a model, and I won't do male and female, I'll do urban and rural. If you're going to have an actuarial estimate to say that urban drivers should pay 20% more than rural drivers, you've got some statistics that back that up, and the statistical analysis has to be done in such a way that you're actually pointing towards the population parameter, right? There's a real number. You don't know what it is, but you know that these estimators can point to it. And we see that in 2 places. One is the actuarial standards of practice, which number 12 says we need to reflect different material differences in the expected cost. And then the statement of principles down below say a rate is an estimate of the expected value of your business costs. So you've got to be shooting for unbiased parameters, or I'm sorry, unbiased estimators of population parameters. That's where you're headed. Because if you're not, then pick anything. So you think about this. If you didn't know anything at all about rolling dice, and someone said, give me the population, give me the estimate of what the probability of a 7 is. And someone says it's pi over 18. Well, that's close to a sixth, right? And somebody does the experiment and comes up with something really good. You can't, pi over 18 is it's an estimator, but it's a bad one. So what you've got to do in these statistical models is be able to separate out the good estimators from the bad estimators. And what happens is, as I turn my notes around here, the current actuarial practice for dealing with missing data can give you bad estimators. And the statisticians have come up with ways to get you good estimators. And the challenge that we have going forward is to get these methodologies, which I'm going to explain to you at a high level. I'm putting together a presentation for the rate making seminar next year in March, trying to write a paper. This is what you should do going forward, actuaries. Their approach is this. Think of gender again. You've got male, female, or urban, rural. You know people are urban, you know people are rural, but there's a bunch of people that you don't know where they are. So now you run your model and you have 3 categories for territory: urban, rural, and unknown. Well, the use of unknown like that in a model can bias your estimates. Okay, so let's do a simple example just to show you some numbers. Okay, so here's some actual insurance data from the references down at the bottom. It's from Generalized Linear Models for Insurance Data. It's a nice little book if you want to get your feet wet on generalized linear models. But here's some actual data that they gave us age group, and I just grouped it together, and it does what you think it does. Younger ages have higher claim frequencies than the older drivers. That in itself is pretty straightforward. So now, before generalized linear models, the way actuaries would make rates, say you wanted a rate relativity for Class B. Well, they're going to take that frequency of 0.17. They're going to divide it by the Class A relativity of 0.2, and 0.17 over did I say 0.12? 0.2. 0.17 over 0.2 is 0.85. So we would say if we're going to charge Class A $1, we're going to charge Class B 85 cents. And that went on for a long time, and that worked. That's what's called one-way analysis. The actuary would do that for age. And then they would go to territory, and they would do that same thing for territory. Gender, anything they wanted to rate on, they'd get their data, they'd aggregate it into these tables, and they'd get all these estimates, which were great estimates, and then they would get rate relativities out of it. Okay, remember that 0.85 because I'm coming back to it. Now run a simple frequency generalized linear model on it, which for those of you that are technically oriented, I ran a Poisson GLM just on age group with a log link. Those are the results I got. Okay, you get an estimate, you exponentiate the estimate, you get a relativity. Class A, age group A there doesn't have anything because that's what we're comparing everything up to. So the generalized linear model told me that for Class B, we need to charge 84 cents compared to $1 for Class A. Okay? Now, you're not going to do a bunch of generalized linear models on each risk characteristic. What you can do is you can put all your risk characteristics in all at once, get rid of this one-way analysis, and get estimates for everything at once. The mathematics behind it actually kind of just works its way out and says, here's everything, which is a great improvement because the old one-way method actually would overcharge people or undercharge people because you ended up multiplying estimates together, okay? But your 0.844 is close to the 0.85 that we got from the earlier method. Okay? And what's important to remember here is we don't know any population parameters. We don't know the true number, right? God might know, but you know, God's not one of us. At least I think that's how the song goes, right? So now what I did is I took that data and I added a bunch of missing data to my data set. I just randomly just selected. That'll come in later when we talk about missing data mechanisms, okay? Grouped them, and here's what we've got. Now we've got this category down at the bottom. So people that were missing had a claim frequency of 0.15, right? 15 claims per 100 exposures, something like that. This is the type of thing that you would see. Remember in the beginning when I said if you get some data, a bunch of data, and you've got missing stuff, you would do these kind of summary statistics to see what is happening with everything. And so now you're looking, it's like, well, okay, do the missing people, their 0.15 frequency, what does that mean? If you run the GLM on it, the missing, actually I told you there, missing frequency is the overall frequency. I'll tell you why in a little bit. Now run a GLM on it. Yep, I got a clock here too. Thanks, Scott. I got 2140. Okay, so we run the same GLM assumptions, and we get these estimates. So before we had, remember when we just did a one-way analysis, that relativity for B was 0.85. I ran a GLM, it was 0.844. Now I've run a GLM with missing data, and it's 0.853. So the standard error measures, say, how good the estimate is. Small standard errors are better. Okay? But the key here is each of those estimates / relativities are pointing to the actual population parameter value. The question you need to ask yourself, and this is the simplest way that I've come up with to explain to people why missing data in GLMs like this isn't a good idea. It's because there's no missing, we've got a missing statistical estimate of, say, 0.752 relativity. What's the population estimate? What's the population parameter for people that are missing in age? There isn't one. Everybody's got an age. So you've built a model, you've got estimators, and they're not pointing at anything that exists in real life. And what that's called is the fallacy of reification. And I'll give credit where credit is due. This was told to me by our actuary friend Gennady out in Nevada. I didn't know there was a name. I just knew that there wasn't a missing population parameter. So it's when you think, you've talked yourself into believing that this abstract concept is actually real. Okay, so that's the simplest explanation as to why you shouldn't model with missing data the way that the industry has been. Okay, now if we compare it, and this is kind of a little technical. We've got our difference just focusing on age group B there. We've got a 0.844 and an 853. That changed, but the standard error, the thing you use to get confidence on your estimator, it got bigger. Now, a reason why it got bigger was because you had fewer observations in that bucket. If you go back to here, you had, 5,892 observations in Class B. Well, when you added missing data, now it dropped down to 4,677. So things are going to happen when you do that, and one of them is the standard error is going to get bigger because you have smaller data, smaller volume in data. If you remember before with our dice rolling, where your graph went up and down and up and down and up and down, and then as you got more data, it started zooming in on the actual number. Okay, so the standard error measures the variability, you introduce missing data, you're increasing uncertainty, so therefore the standard errors are going to reflect that. Okay, now, in this particular example, because it's a simple example for you guys, you may be shrugging and saying, well, okay, they're close enough. But in general, when you use this method in your models, the bias is unpredictable, which means it's not always higher, it's not always lower, but you are introducing bias into your model. So your estimators aren't pointing where you want them to be pointing. Okay, and this reference was shown to me a few months ago. I want to give a shout out to Frank Kwan at the University of Illinois, Urbana-Champaign, who was nice enough to do a little bit of research to get me started on this. Okay, so there are three ways that statisticians characterize missing data. One is called missing completely at random. The other is called missing at random, and then if you're not either one of those, you're missing not at random. Okay, I'm going to give you an example, but those are the three categories. Missing completely at random, your cat walked on your keyboard and deleted some data. The chances of you having something missing doesn't depend on the data. Excuse me. The chances something missing doesn't depend upon your data at all. It's just some probability distribution. Okay? The missing data that I introduced in the examples I just showed you, that's missing completely at random. I don't remember what the probability was, but I just grabbed ones and threw them into the missing bucket. Missing at random, the missingness, the probability that the data is missing, depends only upon known values and maybe some probability distribution. So for example, with the insurance score, that I talked about in the beginning, 998s and 999s. Well, when that came out in the early 2000s, the assumption was older people got thin hits and no hits because they didn't use credit. And so the probability of being missing, say, with credit scores, depended only upon the age, which you all knew. Okay? The third category is kind of the default. If it's not one of those guys, then it's this. Okay? Missing not at random, right? The probability of being missing also depends upon another guy being missing. This is what we see in industry data sets. And the example I've got here, and this happens all the time. They don't know the number of stories. They don't know the number of bedrooms. They don't know the number of bathrooms. But you can look at that data set and you can say, the probability that the number of stories in that house is missing, when I know that the number of bathrooms is missing is 1, that's missing not at random. Okay, the missingness depends upon other missing variables. Okay, yeah, most of the missing data we see is missing not at random. Now, so we have an NAIC model review checklist. I'm sure all of you have seen it, that we go through. We don't ask this question. We haven't had the conversation among ourselves yet. Should we start asking this question? Please classify your missing data mechanism. In part because I think at this stage of the game, it would just throw things in, into utter chaos. I will tell you later on what one of the questions that we have been asking in regards to missing data. Okay, and I got 12 minutes. One modeling approach is to model, just delete all the records with the missing data and then run your model. That's what's called a complete case analysis. It gives you unbiased estimates. All that stuff I was talking about where you're modeling with missing as a factor level, that all goes away because you're only using data that you know. Okay? That's the default, for example, in R. You give R a data set and age group is missing, it's just going to ignore those records. It's going to run the model. It's going to say, here's a warning for you. We deleted this many, or we didn't use this many records because there were NAs in it. Right? It is an unbiased estimate because you have a decreased number of records. Your standard error is going to be a little bit more. But in general, it'll give you a good estimate. Now, this is where things get really dicey, and I'm avoiding all the technical stuff here. Okay? There's something that I took an online workshop on missing data analysis, and the instructor, who was a statistics professor at UCLA, he kept referring to these as the big 3. There are 3 statistical methods that are generally accepted that allow you to model with missing data in your data set. In other words, not do a complete case analysis. Full information, maximum likelihood, Bayesian estimation, and multiple imputation. They produce under missing at random. Right, remember we have missing completely at random, missing at random. Everything that's missing completely at random is actually missing at random. So you've really only got the 2 categories. They give you comparable results, but you can't use missing not at random. Okay? There are software limitations because of the types of models that actuaries use that aren't used as much in the clinical research, say, space. I asked him about Tweedy distributions. He had no idea what I was talking about. So things like logistic regression, all those will work. Normal distributions, you know, just regular old linear regression, those will work. The full information maximum likelihood estimation and the Bayesian estimation. And they're kind of, I don't have my head around them yet quite technically. That's one of my next couple months projects, is to try to get that down well enough to be able to explain it. Multiple imputation is, however, fairly, it seems to me to be the way to go. Okay, and what multiple imputation does is you create what are called plausible data sets. And you run your model on a group of plausible data sets. And then you do some averaging on your model results, and you get some estimates that are actually unbiased. And you get a standard error that corrects for the fact that you have missingness in your original data set. Don't worry, we're in the home stretch. I'm going to see if Cal Raleigh is going to break Mickey Mantle's record tonight, so I'm in a hurry to get out of here too. Missing not at random, there are no well-defined standard tests. This is a quote from, you know, one of the 3 books. If you got the slides, there's a reference at the end. This is one of the 3 books that there's a reference there. So what they recommend, and this was Craig Enders was the professor that did my workshop, do a sensitivity analysis, which means tell me, so from a regulatory review standpoint, tell me a story. Tell me why you think this model works for this data set. Do a complete case analysis. Do a complete case analysis and run a GLM like I showed you that you shouldn't do. And then show me that those 2 approaches are close. That's the kind of question that we've tried to start asking in our model reviews, is tell me what your model would look like if you deleted all the records with missing data. So that's kind of it. That's the state of where we are on how you should be modeling with missing data. I think a key takeaway is nobody's forcing a company to model with missing data. None of the regulators are saying, I need you to model with 40% age of home missing. Nobody's saying that. That's a choice that they make. There are statistical methodologies for handling missing data like that. And maybe you need to start doing it. We asked a question one time, and this is kind of a little expanded version of a CASTIF book club I gave back in February, right when I first started learning some stuff. And we asked down the road, when they used the missing factor level approach that I showed you, give us a reference. We knew there wasn't a reference that said it was okay to do it, but it was like, give us a reference. They referenced my presentation saying this is not a good thing to do. So we got a ways to go here. So here are some questions that you should be asking as a regulator reviewing model. Tell me about how much missing data you have. Why is the data missing? What methods did you use? Did you do a complete case analysis? Did you use one of these other methods that I just mentioned? What assumptions are made about the missing data mechanism? Okay? And the multiple imputation, which is relatively straightforward to implement, Does that give you similar answers to, say, complete case analysis? And if not, why? A major thing that I see interest in model filings is nobody's telling you a story. Nobody's telling you why. We want to model with this because we think this is a good thing to do, because it'll help us understand this, or this, or this. And we do ask for rational explanations for all the rating variables. I won't go into the answers we get for that. So here's really kind of your main point. You're going to get biased estimates if you're not careful modeling with missing data. Okay? If you're going to make something up as you go along, which is kind of what, let's just, male, female, missing. If you're just going to make that up in your model, you're going to run into trouble. And that there are more sophisticated approaches. And hopefully we'll try to get the actuarial community moving towards the missing approaches. Questions, comments? I'll leave it on the references in case you want to get a picture. Chris, I saw you taking pictures back there. If you want the slides, let me know. Shoot me an email, I'll send them to you. I'll take all the comments out first, but yeah. Anything? We got one back there, Miguel.
Hi, I'm not an actuary. I'm an analyst in market conduct. And I was wondering, as far as your presentation, is it all involving the creation of the model and the rating factors, but not necessarily the application of it to one individual person or home?
Yes, if I'm understanding correctly. So the first point I made about rating, there are companies that want rating factors to say rate somebody. They don't, and I don't want to characterize the industry as a whole, but we're seeing instances where, and I'm hearing anecdotal stories from regulators that say, hey, they just don't want to go out and look and find out what the characteristics of the home are. We just want to charge them if we don't know.
Correct.
This is more, if you're an actuary and you've made the choice to model with missing data, well, then there are things that you're going to need to start doing to get correct models, because the models that we've been seeing, and it's not the actuary's fault, this is, this just kind of evolved over time. The models that we see can be statistically unsound.
That's what I understood. So
Okay.
Then my next question is, so you have, even if you have a model that was used with just created with just the complete information files.
Okay.
What happens if they want to run the model to rate a particular applicant, and that applicant now has a missing piece?
Okay.
What happens? Do we suggest that that person doesn't get rated using the model, or what do you know about that?
So the models aren't run on an individual policyholder basis. The models are run to get rating factors to put into the rate manual. So if somebody shows up at an agent's office and they want to rate somebody and they don't know how old the roof is, well, then they need to find that out and look up the proper age in the rate manual or run it through their rating engine. Am I getting that? Is that answering your question?
Yeah, you know from your presentation that there was missing data, and there's more people out there with missing data coming in.
Right.
Yeah, so.
They shut me off. No, not quite. Yeah, you get rating factors from models, and then once it leaves the actuary's hands, the business use of whether or not somebody that they want to sell a policy to is not really an actuarial question anymore. Does that help? Okay. Okay, yeah.
So when you're creating these, when you're doing multiple imputation, you're creating multiple plausible data
Hold on, just so that we can get people in audience, and this is probably the last question we can take, Kevin.
So when you're creating these multiple plausible data sets, besides taking like the average of the variable, how else are you supposed to create these plausible data sets, right? I can think an average makes sense to replace as an imputation, but.
There's a whole theory on that.
Oh, okay.
Whether you're missing one, whether you're missing two, whether the missing are correlated. Are you familiar with R? Okay, there's an R package called MICE, M-I-C-E. Multiple imputation chained something. Chained equation, somebody said. Yeah, so yeah, there's a book that goes with it and it explains it all. I'm not an expert on that. I haven't gotten that far down the line, but yes, there are ways to build those plausible data sets. Okay? Well, thanks.